Okay, so on to the next lecture, and we're going to talk about something a little bit different now. In particular, something called resummation, something which gets used a lot in collider physics. And so I'll try and give you an example of what it is and how it happens. So again, I'm going to stick to the example of 2e plus e minus, just because it's a simpler way to introduce these concepts. But again, it's very much relevant, as I say, for the LHC, and I'll give you an example of that at the end, in fact. But we stick to e plus e minus for now. But as I say, the basic concepts carry across to the LHC. And so what we're going to consider is something called an event shape. So let me define that. So this is essentially a global measure of the event, the collision event. And this is something which you can define either experimentally by taking the particles you actually experimentally measure and sort of doing something with them, some sort of algorithm essentially, but also something you can do theoretically in terms of the kind of partons in your calculation. And what we're going to consider is one example, although you'll go through some other ones in the problems, but we'll consider one example which is rather specific to e plus e minus perhaps, but again, it's just an example, as I say. So this is a classic observable, it's called thrust, it's a classic observable, in particular for precision QCD tests at LEP, the Large Electron-Positron Collider that sat in the LHC tunnel before it was the LHC. Okay, so let's define it, first of all. Let me then tell you what this means. Right, so that's what it is. So we imagine we've got some event. Think about it theoretically, probably simpler. So just a load of partons, quarks and gluons that you've calculated. But again, these can be particles as well. Put 4 there, but they can be as any number you want. And we're defining some vector, 3 vector n. And what we're doing is you would consider all possible directions it could take. And then you're going to calculate this object here, which is the dot product of that n, with each of the particles in your event. Then you take the modulus, sum that up over all the particles and divide by this thing here, which is just the absolute values of their momenta. And so there's going to be some orientation of n that will maximize that, and that's what's called the thrust. So again, this is the sum over all final state particles, and I'll give you a simple example in minutes to show you the kind of thing this means and why we've introduced it. So this would be the partons in our theory calculation, and then is a unit vector. So let's give an example. The simplest example, which sort of tells you why it's called thrust indeed. So back-to-back QQ bar. It's just our leading order process we had before. And those will be back-to-back in the center of mass frame, like so. And now clearly the thing which is going to maximize this dot product there is just going to be to take n to be in the direction of the axis of the QQ bar. It doesn't matter if it's actually pointing up or down in this picture, we'll get the same result, but it just has to point in that direction. That's going to maximize it. And then the corresponding value of the thrust, of course, then cos theta nq, the modulus of that is going to be the modulus of cos theta nq bar, which is just going to equal 1. It's pointing along their directions. And so that's just going to give you the sum over the modulus of the p's over the sum of the modulus of the p's. It's just going to be 1. Okay? So therefore, thrust equals 1. So this is why it's called thrust, because it sort of tells you about how sort of pencil-like kind of thrusty, if you like, the event is, and T of 1, something which is purely going along one line. Whereas for a sort of spherically symmetric high multiplicity event, you'd have t of a half. And for 3 particle event, it can take a range depending on where how they're oriented, but it has this range. And I'm not going to justify those because there's some exercises on that. Okay, so let's start. What are we going to do with this? Well, let's start with our expression again, QQ bar gluon. Let me rewrite it in a slightly different form. I'm just going to keep a load of prefactors and call them sigma naught, just because it simplifies the discussion. The rest is as before, so x1 squared plus x2 squared for 1 minus x1, 1 minus x2. And yeah, this thing here is essentially, well, it is the QQ bar, the leading order cross section. So it's NC FQ squared 4 pi alpha squared over S. But it's just a prefactor. That's all we kind of need to know for now. So I'm not going to go through the details, but with a little bit of work, one can think about what the thrust is in terms of these x1s and x2s. We've got a 3 particle event. You can express the above as a d sigma d thrust, dt. So, for each event, one's going to have some direction of particles with the corresponding x values, and essentially your dx1, dx2, the thrust is going to be, one can easily argue, the maximum of the 3. Let me write that again. That's not very clear. The thrust is the max of x1, x2, x3. Essentially, you choose your axis n to point along the most energetic particle, and then it's just given by x. So a little bit of work to show that, but essentially, right, one just does that. Okay, so sigma QQ bar G, but with a delta function of that. Okay. So instead of having a double differential cross section in terms of x1 and x2, one has a single differential thing. And for every value of the thrust, one then implicitly has an integral over basically one of the momentum fractions. Will all give you the same thrust. So after some work, you get this. So gets this. So let me write it out in all its detail, just because I'm going to point out a few of the elements of it, but I'm never really going to use the full expression. It's not particularly pretty. There it is. Minus t. So this is clearly a messy general expression, but let's consider for simplicity, and because it's going to be of the most interest to us here for what we want to show, the t goes to 1 limit of this expression. Okay, so we don't want it in this full generality, although I've given it for you, but let's consider that limit. In particular, I'm going to take 1 over sigma naught d sigma dt for a reason that will become clear in a minute. So that goes, as t goes to 1, well, okay, I mean, you've got, that's obviously going to go to 0. That's going to go to log 1 over 1 minus t. That stuff up the top is going to give you a minus 3. So, and that's obviously minus log 1 minus t. And so when the dust settles, then you just get this minus cf minus sine alpha s over 2 pi. And you've got a 2 times 2, so 4 log 1 minus t, 1 minus t plus 3 over 1 minus t. Okay. Which we can see clearly diverges as t goes to 1. So divergences abound again, but we've seen this before and it has exactly the same interpretation. So nothing new here, just re-expressed in a slightly different way, but we've seen this before. In particular, remember, I've just told you that thrust going to 1 is precisely when things are back to back. So, in particular, is precisely, let me draw them out. Do that in a different color. A gluon there, or a gluon there, or a soft gluon like that. Okay, and those all give you that back-to-back configuration, that thrust going to 1. So one's picking up those collinear and soft singularities again. Remember, I've only calculated. I've started with the expression for the real cross section here. Right? So these are precisely where the collinear and the soft gluon emission in QQ bar plus gluon is relevant. Okay, so it's no surprise. Now, again, as before, I've not included the virtual yet, so nothing's infinite, everything's well behaved. So what's the problem? So if we're only interested in A plus E minus go to hadrons, then we include, the virtual, and that's it, everything is okay. But the question really is, what if we're interested in something more than that? So what if we want to ask other questions of our theory? So for example, indeed, this is what we're going to ask. So if a gluon, forget about the soft collinear region, if it's emitted with a large enough energy and not collinear, according to some measure, we're going to have a 3-jet event. Jumping ahead a bit, I'll talk about how precisely we define jets later on, but at least to give you some idea, or you probably will have some idea that these things are then sort of separated, collimated sprays of particle, and if that gluon is separated enough from the quark and the antiquark in your detector, you'll see 3 clearly separated jets. Okay. And so a natural observable is then the fraction of events that are 2 or 3 jets, like I would have 2 or 3 jets according to what our definition of a jet is. Well, I'll say a little bit about that in a second, which I'm going to label R2 and R3. Okay. So R2 plus R3 in our calculation is going to equal 1 because it's either 2 or 3. That's all we've got in the calculation. R2 plus R3 equals 1. Okay, so to do this, we need to introduce something which tells us what we define to be 2 and 3 jet-like, clearly. So we introduce a resolution parameter. In order to define what we mean by 3 jet-like and versus 2 jet-like. So again, let's draw some cartoons. I did that before. And let me draw this one. Like that. Now, one might just stare at that and say, yeah, that's a 3-jet event. What we want to call that a 3-jet event, it's clearly got 3 well-separated particles, but it's a little bit less clear by eye for the second one. And essentially then that means that you just need to have some resolution which tells you that if they're if the quark or the anti-quark and the gluon are closer than this resolution scale, we're going to call that one jet. And if not, we call them two jets. And therefore, with the third particle, a three-jet event. So three-jet, question mark. So let me draw that again. Let's call that tau. That's our resolution parameter. And essentially, if the thrust is bigger than this tau, then we're going to say it's a two-jet event. And if it's less than it, we call it three-jet. Remember, tough thrust of one is purely back-to-back, so that's definitely three-jet. And then you have some allowance according to how small or large you make tau for the emission to not be completely collinear, completely soft, but still nonetheless one wants to call that a two-jet event. But if otherwise, we call it a three-jet. And of course, as we'll come back to this, this is of course very comparable to the jet radius r, but defined in a different way. And for the two-jet case, anything that we call two-jet will add in the virtual corrections and everything will be finite in the end, all right? So those infrared singularities will go away. But we don't need to worry about that here. That's not our concern for what we want to discuss. So let's define our three-jet fraction as a function of this tau. So we integrate up from 2/3, which is, you'll show in the exercises, the minimum value this thing can take for a three-particle event, 1/sigma-naught, we just integrate it up. Okay. Now, I mean, I can take the general expression if we wanted to, which is up there, and integrate it, but it's a little bit complicated to do, certainly by hand, so we don't want to do that. But what I'll do instead is focus on, again, a particular limit, because that's where we're interested, and then I'll comment on it in the end. So instead of focusing on that top expression, I'm just going to instead integrate up that bottom one. So I'm going to focus on the thrust goes to one region, and then I'll justify that in a second. So let's focus on the t goes to one part. This then equals, in that region, so approximately CF, well, no, it is equal, if we focus on the thrust goes to one limit, to minus, minus alpha minus CF alpha s over 2 pi. And then we've got the integral again. And yeah, let's stick that in again, just to be clear. Oops. Plus 3 over 1 minus tau. And yeah, clearly. Oops, sorry, my bad. Let me write that again. Those are not taus. 1 minus t, 1 minus t dt. Okay. This equals, you can integrate it up easily enough to let me do it, just to be completely clear that this is indeed what happens. So you get 2 log squared, 1 minus tau now, plus 3 log, sorry, no, not 1 minus tau. Should have chosen letters that look less close together. 1 minus t and 1 minus t there. And that's in the range, sorry, yeah, 2/3, 1 minus tau. Okay, so I've just used sort of known integral for log x, particular, you know, that log, the integral of log 1 minus x over 1 minus x is equal to minus a half log squared 1 minus x. So that's that. And this is equal to, therefore, so R3 of tau, again, in this limit, CF alpha s over 2 pi, 1/sigma-naught, 2 log squared, now it is tau, because I put in the limits, plus 3 log tau, and you get some other stuff. Let me put it in just for completeness, but we really don't care about it. Some other numbers. Now, if we kept the full expression, and the reason why I've only kept this to keep it simple is that if we kept the full expression, it would look the same, right? It would just be of the same type, so exactly like that. Apologies, let me get rid of them. They shouldn't be there. It would be of exactly the same type, but we'd have the same logarithms. Like so. And then plus some stuff which is regular as tau goes to 0. Okay. So one could do it, you'd end up with it, but the point is that those logarithms are there in tau in the full expression as well, because they're coming precisely from the t, the upper limit, essentially, of the t integral. So we've got a perturbative QCD prediction for this jet fraction, and now we ask, so what about the tau goes to 0 limit? So this justifies why, when I did the calculation, I only kept the t goes to 1 part of the expression, that approximate, that part in that limit, because in the end, what we're interested in is precisely the region where tau goes to 0, where our resolution parameter becomes small. Well, then clearly we've got these logs in tau, right? So then the log squared tau in particular dominates. And here's the bottom line, that's what you get, okay? 2 times log squared tau. And well, yeah, R2 is just 1 minus that, so 1 minus CF alpha S over 2 pi 2 log squared tau. And so for small, but I'm not, I'm just considering how it looks in the limit that tau becomes small. I'm not actually setting it to 0, but just in that limit that tau goes small. So it's a perfectly, in principle, well-defined region. Nothing is infinite. The log is, I'm not taking the log of 0. I'm just saying, imagine tau's 0.1 or 0.01 or something like that. Let's take tau to be quite small. Well, then this log of tau is going to be big, right? That's the point. So for small, but non-zero, so nothing's infinite, tau, our fraction, our predicted fraction, of 3 jet events is arbitrarily large. In fact, greater, less than 1, or something like that. So completely nonsensical. And indeed, R2 is actually negative. Well, yeah, and indeed, R2 is negative. So certainly nonsensical. So what is going on? Well, the solution, again, first of all, to emphasize, you include the virtual corrections and they will go into the 2-jet case rate and everything will be finite. Nothing is infinite here. Okay, I say I'm just numerically taking tau to be small, but nonetheless, you're getting answers that look nonsensical nonetheless. So what's going on? So the solution here is this. We are expanding in alpha S, so our prediction is a perturbative expansion, and therefore we can only trust our results in the regime where the expansion is reliable. And here we have R2, if you like, R2 of tau, R3 of tau, let's say R3 of tau is equal to CF alpha S. Actually, no, let's stick with R2 of tau, makes it a little bit clearer. So R2 of tau, the 2-jet fraction, is equal to 1 minus CF alpha S over 2 pi times 2 log squared tau. That's our leading order result, right? That would just be our prediction. If you just had a QQ bar in your prediction, well, then it's always 2 jet-like, so that's the one. And then we have the NLO correction, okay? Coming from allowing a gluon to be emitted. And so the NLO term, we've got alpha S log squared tau. It's a lot bigger than 1, and therefore it actually becomes bigger in the leading order term, which of course you can't have if you want a reliable perturbative series. You're just in a regime where apparently perturbation series theory is worth breaking down. So we have a breakdown in perturbative QCD, which is driven by soft and collinear emission. Essentially, because if tau goes to 0, if you make tau small rather, you've got a very stringent requirement on there being no extra radiation, whereas you're never strictly taking anything, allowing kind of completely 0 energy gluons in your calculation. You can have sensitivity, let's say, in your 3-jet rate to rather soft gluon emission or rather collinear gluon emission if you really have a very small resolution parameter within which to keep things just being 2 jet-like. And so whereas essentially the real and the virtual actual singularities cancel, you have a kind of residual logarithmic dependence when you really push things into that regime on this tau. But all is not lost. So without justifying it, but we will find this. So R2 of tau equals, as tau goes to 0, 1, so that's what we've just got, plus a half dot, dot, dot. So perturbation series is certainly breaking down. Perturbation theory is breaking down. Each term on top of the next is bigger than the last one, but the above is nonetheless a Taylor expansion of something. Particular e to the minus x equals 1 minus x plus x squared over 2 dot, dot, dot. Okay. And therefore, even though we can just by observation essentially say, well, actually, we know the all orders result of this logarithmic term, and therefore we can include it in our prediction. So we know this contribution that goes like log squared tau, which will always appear at each order in a perturbative series, we know it to all orders in alpha S, i.e., I'll write that again. I.e. exactly. Okay, so R2 of tau equals, as tau goes to 0, just the exponential. Remember, I've just said it's a Taylor series of e to the minus x. There's x, CF, alpha S, blah, blah, blah. So minus CF, alpha S over 2 pi, 2 log squared tau. And order by order, this will jump around all over the place. But the exact result, exact in this limit, is perfectly well behaved. And in particular, actually goes to 0. R2, the 2 jet ray, as your resolution parameter goes to 0, the exponent there goes off to infinity. You've got e to the minus infinity, that's 0, goes to 0 as tau goes to 0. So what's the interpretation of this? Why is this happening? Well, let's recall our NLO term. R2 of tau, 2 jet rate, equals 1 minus CF alpha S over 2 pi, 2 log squared tau. Then we can interpret this CF alpha S over 2 pi, 2 log squared tau, sits there as a sort of what we call a naive probability, naive in the sense that it's what we get out from just calculating the first order and perturbation series. We've just seen that that's not enough, so that's why we call it naive. So a naive probability of radiation leading to a 3 jet event. So obviously 1 minus it, 1 minus that thing is the 2 jet rate, and therefore that thing is the 3 jet rate, and it's either 2 or 3 jet like at this order. And so in other words, this thing I've just told you, this exponential of minus CF alpha S over 2 pi, that's the thing we get. It's precisely that. And in the jargon, this thing is called, by the way, a Sudakov form factor. Sudakov is just a physicist name. It doesn't add anything to call it that for the sake of this discussion, but maybe one day or previously you've seen that word mentioned. Well, this is what it means. But more physically, put that in brackets, this is a Plassonian probability, right, of no emission. All right. So just try and stick that at the bottom. Of course, the probability of having n emissions when you've got some lambda, that's your parameter in your Plassonian probability, lambda to the n e to the minus lambda n factorial, then of course p of 0 emissions is just e to the minus lambda. Okay. So one can think about a Plassonian process for emitting these gluons, if you like, and then this then becomes the 0 emission probability. And so the probability of no gluon emission, no gluon radiation, in that tau goes to 1 limit, tau goes to 0 limit, is 0. And this makes sense physically, because if you look hard enough, if you reduce your resolution parameter hard enough, essentially there's always going to be some extra radiation. That's just kind of what you expect from sort of quantum mechanics, if you like. There's always extra radiation if we look hard enough. So this thing here is the essence of resummations. We have just performed a resummation. Okay, so resummation just means observing that something has this form, or showing that it has this form, which we've not done that here. We've skipped that step, but one can do it. And therefore showing, given that, one can just include all orders, in this case, in log squared tau, by just having something like that. That's the resummation. Okay, resummation, because you're resumming, you're adding up to all orders that contribution, rather than just working order by order. And so that's called resummation. And again, there's the idea that certain enhanced terms in perturbative expansion can be calculated to all orders and this stabilizes the result. this is certainly relevant for LHC physics. I'll show you a few slides on that in a second. So let me just say a couple more comments on that. So one thing to bear in mind here, and the Plassonian interpretation helps to see that, is that Monte Carlo generators, in particular the parton shower, these implicitly perform this sort of resummation, in fact. Let me write that again. And so indeed, one hears people talking about the logarithmic accuracy of parton showers, and that's because they do this sort of thing. They perform this sort of resummation. So, you know, because, again, I've just said, right, the probability of no emission is very low as long as your resolution parameter is large enough. Well, if you imagine starting with the quark, in this case, just the QQ bar, and then showering it, what's your parton shower going to do? It's going to address that with a pretty high probability, with a load of extra things being emitted, extra gluons being emitted like that. And therefore, if one then took that event afterwards there and calculated the jet fraction as a function of tau, you'd automatically see it going to zero as tau goes to zero, because there'd always be this extra radiation generated by the parton shower. And so in that sense, it does the same thing as the resummation. So probability, no emission, is very low. Okay, I mean, as always, I'm simplifying things to some extent, but that's the idea. The other thing is that we have considered the so-called leading log squared tau term here. But let's recall that actually we had something that looked like this. CF alpha S for the 3 jet fraction, 2 log squared tau, that's what we've just discussed, but there was also a 3 log tau. Okay. Now clearly the log squared tau is blowing up faster than the log tau as tau goes to 0, because it's squared up, but still the log tau is also not particularly well behaved. So one has to worry about that at some level of precision. So the 3 log tau in this case is called a single log. And one can should also resum it. I haven't considered that here, but one can do it. Just a bit more difficult, maybe. And so the jargon here, this is all I want to say, is that, again, you might hear these things, is that in this specific case, the alpha S log squared tau, because that's what you get at each order, a log squared tau matching an alpha S, that is the largest contribution, and that's therefore the leading log, LL as it's labeled, and the alpha S log tau, which is 1 logarithm down, so it's a smaller contribution versus the log squared tau, but still enhanced versus just alpha S alone. So it needs to be resummed. We call that a next to leading. And you know, for other processes, it doesn't. One can get further powers down of alpha S's and the logs and so on, and you get next to leading and so on and so forth. But again, that's the basic idea. It's a next to leading log, so N, L, L, like that. So if you see that labeling, that's what it refers to. Okay, so let me show you a few slides to highlight some of that. Let's go to that. So what I'm showing there is just the thrust distribution. And maybe the thing just to, without looking into all of the details, is to look at that bottom plot, and you can see, sure enough, that we've got NLO, NNLO, and so on, which is just the order of the perturbative calculation, but also this NLL labeling, and that's that resummation precisely in there. And maybe a little bit clearer here, actually, I think, is to show it sort of analytically. So here again, one showing the 2 jet fraction versus tau, and one can see that the NLO result in the blue just goes off to negative infinity as tau goes to 0. And then we've got including the Sudakov in the green, essentially, and one can see it going to 0 nicely, and that's exactly that resummation having an effect there. And I promised you that this was relevant for the LHC, and indeed that's the point. So all you need here is that there's some logarithm there of some variable that is becoming large in some region of phase space. And when that happens, that's when you need to do this resummation. So a nice example of that is the Zpt distribution. So the PT distribution of the dilepton pair. If the Z decays to, so here's the normalized distribution against some CMS data. And the point here is that as the PT goes off to 0, one ends up now not in log taus, but log PT of the Z over the M of the Z. And that naturally happens and is again due to these sort of soft collinear radiation effects I've talked about. And one can see the fixed order in the green sort of going off to infinity for the NLO case. And we're also kind of jumping around a little bit for NLO, which is in red, if you just about see that, versus NLO. But then the resummation or else including parton shower has the same sort of effect, nicely turns you over towards sort of 0. In fact, it's the same sort of 0 effect. It's that Sudakov factor again, so to sending you off to 0. And essentially here, the point is that now, right, that the leading order result would have completely 0 PTZ, as we'll discuss. But as soon as you emit extra gluons, you take it away from 0 PT. And so if you demand that the PT goes to 0, that's rather comparable to the requirement of setting tau going to 0. You're putting a very restrictive constraint on extra radiation, and that's why physically you sort of need resummation here as well. Okay, so let me go back to the slides, to the blackboards, and let me start on something else. So okay, let's move a little bit closer to what we do at the LHC. But as I say, as I've just discussed, all of that is very relevant. So not to forget that. But now let's talk about hadronic initial states. And in particular, PDFs. So having discussed some elements of QCD in the final state, let's now move to the initial state, let's say hadron, or actually also hadron-lepton. So I'll start with collisions, which of course are relevant for the LHC, as we know. And so the main question I really want to address here is, I've talked a lot about how you connect your hard scatter to the actual thing you measure. I'll say more about that in the final state, via the showering and resummation and all of that business. But we also have something in the initial state, which is the fact that we're colliding strongly interacting particles. And therefore the question is, how do we deal with that fact? So how do we deal with strongly interacting particles in the initial state? So the solution to that question is conceptually very much the same as before, similar to before. And that that is the factorization, it's a factorization argument, separation, the factorization of the long distance physics which in this case is the binding, the quarks, the gluons into the proton, from the high energy interaction. And again, it's a sort of time scale argument, as we'll discuss. But essentially, yes, the idea is that now all of those sort of effects sort of that one might think you need to worry about how exactly the quarks and gluons are bound in the proton, and one might be sensitive to, one can sort of factor off into one universal function, these PDFs. And the reason you can do that is essentially because the timescale of those non-perturbative binding interactions is much longer than the very short timescale of the hard interaction, which one can then consider to be sort of independent from that, well, up to some caveats, as I'll discuss. So, jumping ahead a bit, for an EP collider, I'll come on to PP. Start with EP, again, just because it's simpler. But really, the ideas are the same to a large degree. So sigma EP to M, some hadronics system, is going to be given like this. An integral dx, some PDF of a proton, which depends on x and q squared. I'll tell you what those are in a minute, times a quark lepton scattering cross-section, plus some terms of order, sort of lambda QCD over q squared. So again, the reason precisely that sort of correction comes in at the end, so higher twist corrections, what they're labeled as in the jargon, is exactly because it's always this timescale argument. And so q squared isn't that large. It's just the photon exchange, the photon virtuality. Then one no longer has this nice separation of timescales. And so that's where the corrections to this formula come in. So yes, FIP are Parton distribution functions. PDFs. And this is essentially the probability, as we'll discuss, of finding a parton with some momentum fraction x at an energy scale q squared, squared energy scale q squared. And again, just to be clear, lambda QCD is the scale at which alpha s is of order 1, so precisely the scale of these binding effects and hadronization effects by the same sort of idea, same sort of argument. But okay, let's do it in a little bit more detail. So I'm going to talk again about something which seems a little removed from PP collisions, but again really sets the scene, and rather than just sort of quoting that result to you, tells you a little bit more concretely about where it comes from. But then all of those ideas, or a lot of those ideas, carry across to the LHC case. It's a nice way to introduce them, let's say. So let's do that. So to understand better what this means, let's consider lepton proton scattering. So DIS, deep inelastic scattering. Let me draw the diagram. Okay, I mean, don't think too much about the fact that I put 2 lines there. It's just a schematic way of drawing the proton. You can put as many lines or in whatever colors you want. It's not, I'm not saying it's 2 quarks or anything like that. And then a load of particles are produced there. That's, I'll label that with a W, tell you what that is in a minute. You could label that with a K and a K prime, although I won't actually make use of those variables. So that's the basic setup. Let's start with some useful kinematic properties, or variables actually. So let's start with some useful kinematic quantities. So let me introduce them. So we've got q squared, which is just the minus the virtuality there in the photon. That thing there is negative. It's a T-channel exchange. And so the minus of it is always positive. So that's basically why we define that. Okay, p squared is is just MP squared, and that we're going to set to 0. So, I'll say that in a minute, but let me put that there. And W squared is Q plus P all squared. So that's the invariant mass of whatever's the dissociation system, which would be a load of particles being produced afterwards. So this is the squared invariant mass of the hadronic system. And this is by definition greater than or equal to MP squared. I mean, it can be equal MP squared, then it would be elastic scattering, but it certainly has to be greater than or equal to it. So DIS, what defines DIS? Because there's all sorts, as I say, you could have elastic electron proton scattering, that's certainly a thing. But what we're interested in is not that, but rather the case that the Q squared is a lot bigger than MP squared. So we call that, that's the deep, if you like. And as I say, it's inelastic. So we also want the W squared to be a lot bigger than MP squared. And also, so other useful quantities. Is the Bjorken, as it's called, Bjorken X. So that's, again, named after a physicist who sort of made use of this concept, or this variable rather, and the so-called inelasticity, Y. And so the point is here really that all of these variables one can get out by measuring the energy and the angle of the scattered electron in this case. So that's really your probe, and that will then, one can easily enough show that that gets you out these things. So the Q squared, for example, is clear enough. It's the full momentum transfer to the electron as well as the proton, so one can certainly measure that, and you can also get out the other things as well from the precise kinematics. And yeah, so that sort of sets up our problem, if you like. Okay, so next time I'll say a bit about what theoretically we can say about this process, having sort of set up the kinematic variables. But I'll stop there for now.